All right, here we go. I'm going to try, you notice I got a little different thing going on here with the board. I'm going to try to, I had another class that wanted me to try this and they liked it way better with the black background. You can decide. Let's have a look at this problem. We want to do a sketch of this rational function. Okay, why is it a rational function? What's the definition of a rational function?
Because it's like a function divided by something.
So, and those, how would we classify those two functions? What do we call it if it's a sum of a bunch of terms, and each term has a coefficient and a power of x? What's our word for that kind of a function? Polynomial, yeah, so it's a ratio of polynomials, good. Okay, so what are we going to do with this? If we want to do a sketch, remember, we're not trying to do a 100% accurate graph, but we just want to get an accurate, we want to get a representative sketch. What are we going to do to this function in order to get our sketch? We're going to factor it, good. Okay, so let's factor this thing. What do we get on the top? What does it factor into? What numbers multiply to -6 and add to -1? Okay, everybody good with that? Right? What about the bottom? Oops, positive for -1, is that right? Okay, so tell me something about that. So factoring the top is, let's start with the bottom. Let's always start with the bottom. So I'm gonna take a slightly different approach to this than we did last week. The first question I'm gonna ask you is, what's the domain of the function? Domain meaning set of all the input values, the x values that work for that function. Okay, we're gonna start with the default that it's all values, right? It's all real numbers. But are there any values that we have to exclude? Before we get specific and look at the function, I want to know what are the two rules that we have to always follow. And this is where we're going to look to see if maybe there's some values of x that need to be excluded. What's one of the rules for real numbers? What's one of the things we can't do? We can't divide by 0. Okay, what's the other thing? Okay, even root of negative number. Well, there's no radicals in here, right? There's no roots. So that one we can cross off the list. But dividing by 0 is something we got to be careful of. Are there any values of x that would cause the denominator to be 0? 1 and -4. Okay, so those are the numbers we have to exclude from our domain, right? So I'm gonna say that. So x is not equal to -4 and x cannot equal +1. Okay, why? What's going on at those places? The examples we've looked at, what's always happened when we've had zeros in the denominator of a rational function? What are those corresponded to on the graph? Asymptotes. Good, they've been vertical asymptotes. Okay. There's one other possibility that we'll see in the next example, but for now, we know that those are places where the function is not defined, and we're just going to settle on those being asymptotes for now. We'll look at one little tweak of this, like I say, in just a second, where there's one other possibility where they're still going to be excluded, but they're not asymptotes. Okay, what about the numerator? What do the zeros of the numerator do for us? If I've got a fraction, we can't divide by 0, right? So now those are the x values we must exclude from the fraction. Dividing by 0 gives us, it blows up. It gives us an infinite output, and infinity is not a result we're comfortable with. The world doesn't work with infinities. Math doesn't work with infinities. That's why these numbers are disallowed, because they cause this function to explode, and we get infinite results, and infinity is not a number, right? So that's not a legitimate output. What about the zeros of the top, though? What's the behavior of a fraction when the numerator is equal to 0?
It crosses the x-axis.
Okay, that would be the value of the function would be 0, right? And that just means the y value, right? So those would be the x-intercepts. So those are going to be at +3 and -2. Okay, so if I wanted to sketch a graph of this thing, then I know already I've got a lot of behavior going on here. That helps me quite a bit, right? If this is we already know that we've got this value at -4 right there. It's got a vertical asymptote. At +1, I've got a vertical asymptote, right? And then we know that the function is going through the points +3 and -2. Okay, and so now we just need to know what's it doing, what else does it do, right? What does the function do as it approaches these vertical asymptotes? Is it a positive infinity? Is it getting shot up to positive infinity or pushed down to negative infinity, right? And so we've just got to check some limits and see what's going on, right? How are we going to know what's going on right here at the left edge of this asymptote? What kind of a limit are we going to take? The limit of the function as x is approaching what? Gabe, what's that going to be? What value? This is -4 right there.
So -4 from the negative side?
From the negative side, good. As x approaches -4 from the left, what's going to happen? Well, let's evaluate this and just see. When we evaluate, in calculus, we'll, once again, the fancy terminology we'll use is we're going to evaluate this limit directly. I mean, we're just going to see what happens to each one of these factors, what value they approach as x approaches -4. And if we need to be specific, we'll take into account that it's approaching from the left, okay? In some cases, it's just not going to be important. Like, for example, up here, Matthew, what are we going to get? What is the value of the factor x minus 3 going to approach when x approaches -4? -7, right? So that's going to give us back, that's going to become, that's the contribution that factor is going to give us. What about, while you're at it, what about x plus 2?
-2.
-2. Okay, so the top is going to be positive or negative? Positive, okay? The bottom we're going to get, now here's the one we have to be careful with. X plus 4, what's that going to be? As we approach -4 from the left, this is the one that approaches 0, but 0 doesn't work. We can't divide by 0. We've got to know, it's not truly 0. Is it a small positive or small negative number? Small negative. So that's going to be a 0 minus. And then what about the x minus 1? -5. Okay, so then that's going to give us back what kind of an answer? If we count all of the negative signs, I get 1, 2, 3, they're all negative. So what's the sign of the output going to be? Positive, and we know because we've got a 0 on the bottom, right? And not on the top, that this is infinite. We get some number divided by 0, which blows up. That's infinite. So plus infinity, and that tells us then that from this direction, it's going up, right? Okay, what about in here? We got to know what it's doing when we approach from the right side. So same kind of thing. Limit of f of x as x approaches -4 from the right. I'm going to get the same value there, aren't I? Right? I'm still just approaching -4. So that factor and that factor and that factor are going to give me back the same stuff, right? Everybody agree? So I know I'm getting -7 times -2 on the top, and this factor is still -5. But what about this guy? As I approach -4 from the right side, what's that going to give me? 0 plus. Okay, so how does that change things, Kristen? What's that going to do? Now, remember, we know I've got a 0 on the bottom and not on the top, so that's telling me infinite. What's the sign going to be? Okay, good, it's going to be negative, because now I've got an odd number of negative factors being multiplied and divided. Yes, sir?
Okay, so if you figure out that it goes up from the left, wouldn't it always go down from the right, or is that always?
Okay, it's a good question. I could make one small change to this function that would tweak that a little bit. What if I did that, for example? It would see what that would do. Then I'd end up with whatever this number was down here, 0 plus or 0 minus. When I square it, it makes it positive. See what I'm saying? So not always. Eventually, as you do more and more of these, probably not this year, but like in calculus, let's say, you'll probably be able to just look at these and say, oh, okay, well, yeah, I can see that because that one's being squared, I'm gonna get, but for now, we don't need to get that, that specific. Okay, so then, on this side, it's gonna go down. And then we'll do the same thing up here. So let's just see, as we approach 1 from the left, what are we gonna get? Let's just see if we can power through this one. So what is going to be the limit of f of x as x approaches positive 1 from the left? I'm gonna get, let's count the positives and negatives. I'm gonna get, what's that? Negative times positive divided by times, and this is going to be the 0 one, isn't it, right? So this is going to be a 0 minus. So what's that give us? I get an even number of negatives with a 0 on the bottom. So what's that mean? Positive infinity. So we know it's going to do something. It's got to go through that point too, doesn't it? So I didn't draw that very well. It's probably going to look, more like that, sort of, right? And then on this side here, it's got to go through that point, same kind of a thing. Limit of f of x as x approaches 1 from the right. I'm going to get the same for the 3 that aren't 0. I get the same signs, but then what's the 0 going to be this time? So that makes it negative infinity, right? So over here it's going to do something like that. Okay, that's all we need for now. Okay, we got the limit. We found the vertical asymptotes. Yes, sir.
So until we get any of the vectors squared with the intuitive to think that's always going to be the inverse.
Yeah. Yeah, and you'll see a couple like that, but okay. So here's the actual graph. Thought I had the actual graph. Maybe I know what it is. There's the actual graph right there. So isn't that pretty much what we got? Right? Look good? Okay? All right, next one. What about this? This is kind of an interesting one. Looks very simple. Okay, what do you think that's going to look like? Any conjecture? What do you think? What do you think that function's going to look like? It's basically going to look like, yes?
Can you just simplify it by, because it's x squared over x, wouldn't that just be like f of x equals x?
Okay, so the suggestion is, could you just write it as f of x equals x? Well, here's what it looks like. It looks like this. Oops. What's that look like? X. So, is he right? Looks pretty much, I'm convinced. Looks pretty good, right? So we could just write that as, we're going to say, okay, how about, we'll write this as f of x equals x. Okay, what's the domain of f of x? Infinite? Everybody agree?
Yeah. There's just going to be a bullet 0.
Okay, okay. What about this x on the bottom? Here's the question, right? Here's the $1 million question here. Does the x on the bottom matter if when I factor in, or when I divide an x away top and bottom, I just get back an x? Let's test it and see. Let's go to the graph and see what's happening at x equals 0. Okay. So if we go to the graph, let's go ahead. I'm gonna put a vertical line at 2, maybe. Okay, notice when I do that, there is a point of intersection there, right? The two lines intersect at 2, 2. Desmos automatically puts a point there because it recognizes that there's an intersection. And we'll watch this. If I graph the vertical line at x equals 0, there's no point there. Did Desmos forget? Desmos never forgets, right? Okay. So what's going on?
Yeah, on your-
It's means that there is no intersection, that the red line is not defined at 0. So there's no intersection. That means the blue vertical line at x equals 0 must be passing through, perfectly hitting a hole in the red function and passing through without intersecting. Okay, so that implies something really important here. That implies that we did something not quite right. F of x is not equal to x. F of x equals x squared over x, right? We could say that's similar to the function g of x. Okay, but g of x is different. G of x is defined at x equals 0. F of x is not, right? So we still have to include in our domain of f of x is not equal to 0. It looks exactly like the line y equals x, doesn't it? Because one pixel isn't going to show up as a whole. But when we graph this thing, what we really ought to do is something like this. For our purposes, we want to exaggerate the fact that it's undefined as 0. And so we're going to put a hole at 0, and then the function goes forever in either direction. Okay? So what's the moral of the story? Let's compare this to what we've done in the past. If we go back and look at these previous examples, every example we've looked at up until now, the zeros of the denominator have not also been zeros of the numerator. And those have always corresponded to vertical asymptotes. But when the 0 of the denominator, and if I write this out as, if I write out f of x as x times x over x, those factors, I have simultaneous zeros, don't I? Those factors algebraically cancel. So what's the moral of the story then? If I have an x value that is a simultaneous 0 of the numerator and the denominator, it is not a vertical asymptote. Instead, it's a hole. It's a hole in the function. Okay? This is what we will call in calculus, we're going to call this a point discontinuity, or a finite discontinuity, because all we have to do to repair the function, there's discontinuity there, right? I've got to pick my pen up momentarily to graph this thing. But to fix it, all I have to do is fill in one point. It's easily fixable, right? If we go back, though, and look at one of these other vertical asymptote types of discontinuities, we call those infinite discontinuities, because I would have to bend an infinite number of points to stitch that function back together. Okay? Just some vocabulary that not really that big a deal now, but we'll talk more about it in future years. Okay, so what about something like that then? Let's try this one on for a second. What are we going to do here? Okay, factor it. Always start by factoring. So what's the top become if I factor it? What can I factor anything out of the top? I can. Right, we always want to try, what can I factor out of the top? There's, well, I mean, so we always, we haven't looked at one of these in a little while, but whenever we're factoring any kind of a polynomial, remember our first step is we always want to see if we can pull out a greatest common factor. We undistribute something. X. Yeah, we could pull an x out of the top one, couldn't we? So if we take an x out, we're left with what? So what's the first term going to give me when I divide an x away? Second term? Okay, and on the bottom? Okay, so what's the domain of the function here? Okay, x cannot equal 0. And what else?
Cannot equal -3.
Okay, I want to know, Ruby, what's going on at 0? It's excluded from the domain because it's 0 of the denominator, right? Okay. What are the zeros of the numerator? X equals. Well, what's this one going to give us?
0.
0, and then this one's what? Positive 5/2, I guess. Right? Or negative 5/2. No, positive 5/2. Right?
Yeah.
But what's important about this? I've got x is a factor of the top and the bottom, which means that 0 is a 0. The x equals 0 is a 0 of both the top and the bottom. So what's that do? That's going to be a hole, right? That's not a vertical asymptote. That's a hole. Right? Okay, what about, Jessica, what's happening at x equals -3? Vertical asymptote, because -3 is a 0 of the bottom but not the top. So that's guaranteed to be a vertical asymptote. All right? So when we sketch this thing, that's helpful, right? That's real helpful. We know that we're only going to get an asymptote here. The rest of the functions can be pretty easy to graph. This kind is actually easier in a way, isn't it? We don't have to deal with so many of those weird limits, right? As we're bumping up against asymptotes. Okay, so let's see, what's going on then? If we were to, we have an asymptote at -3. But if I want to do the rest of the function then, remember what happened when we had a hole. When we had a hole, if we algebraically canceled those out, it gave us the behavior of the rest of the function, didn't it? Like if we went back to this previous example, we know that the function f of x looks just like g of x equals x, except it had a hole at 0, right? So this function here that we're dealing with is going to look exactly like what function?
-2x plus 5 over x plus 3.
Yeah, it's going to look just like that one, isn't it? Right? Only it's got a hole at 0. So wherever that function goes through 0, right? X equals 0, we're going to have to insert a hole there. That's it though, right? So what does that function look like? We can just compare this one to a new function. Let's call it g of x, -2x plus 5 over x plus 3. And in calculus, we will literally talk about this as, and this is the terminology that you'll see in every calculus textbook. These are two functions that agree in all but one point. Seems like it could have come up with a more clever name for it. That's how it's always described. So we're just filling in the hole with this function, right? But we just have to remember that there is a hole there. Okay, so let's look at this one then. All we have to do is just take the limit of this simpler function as x approaches 3 from the left and the right. Make sense? Okay. So what about the limit of g of x as x approaches what? -3 from, how about from the left this time? What's that going to give us? On the top, I'm going to get what?
15.
Some positive number, right? And we can find what the number is. Yeah, it's going to be, what is it going to be? 30, I guess? Or no, 11? 11? But we don't even need to know. We just know that it's some positive number. But it's a macroscopic number. It's not 0, right? On the bottom, we're going to get what? 0 minus. So what's the result? So it's going to be infinity, right? Because I've got a 0 on the bottom but not the top, right? And let's put that away, please. So we know it's going to be infinite, but then the sign's going to be what? Negative. Okay, good. So over here, we know that this thing's going to go down. Okay. What about on the other side? We said we had a 0 at -5/2. So we could I guess we could put one right there. Right? On the other side of this asymptote, we'll take a limit. The limit of g of x as x approaches -3 from the right is gonna be what? Maisie, what are we gonna get on top? Same thing as before, right? Whatever that was, it's some positive number, but on the bottom this time we're getting 0 positive. Yes. Yes. Okay. All right. So then that gives us positive infinity, doesn't it? Right? Okay. And so on this side, it's just going to go something like that. Right? Make sense? Oh, but what did we forget?
The horizontal.
Okay, we haven't talked about that yet. We'll get there next time. But we did forget one important thing. The main reason I did this problem, I almost forgot, is we have to have that hole at x equals 0, right? Whatever the value of the function would have been, and we could check. I could plug in 0 and see. If I plug in 0, I just get 5 on the top and 3 on the bottom. So it should be, I didn't draw this very well, evidently. It should be at 5/3. So that's, I didn't draw this thing very well at all, turns out.
I think it's supposed to be positive 5x.
Say it again. What did I do wrong?
The x-intercept is supposed to be positive.
Where is it? Say it again. I'm not. Show me again. Tell me again.
The x-intercept.
Up here.
No, like at the very top, how we got negative 5/2. Isn't
Oh, it should be positive 5/2.
Yeah.
Ah, there we go. Yeah, you're right. Positive 5/2, not negative 5/2. That makes more sense. Okay, good. That's it. Thank you. So that 0's in the wrong spot. So if we know, see what I did wrong. So the x-intercept should be right there. And so it's going to go like this. And we'd know that the hole, then if we wanted to know specifically where that hole was, it's at x equals 0. But if I evaluate the function at x equals 0, it would be at 0, and then what we say it was 5/3. Right? I could. It doesn't exist on the function. But if we want to know what's the point that is being removed, it's the one that we would get if we plugged in 0 into this function. Right? Okay? All right. So then, how much time we got?
3 minutes.
Okay, I'm gonna save this for, I'll save this for next time. This is really quick, and then we're done. And we're done with Module 8.